Hello everyone. In the previous session, we discussed about what Dockers mean to AI application development. Today, session 2 of this week 2, we will talk about deterministic environments and containerized Jupyter notebook. Now, in the previous session, we saw that the containers are basically isolated by design. Now, if you are supposed to be working on AI application development, you require Jupyter notebook, which is one of the very essential things which everybody uses, right? And we also know that when you work on a Jupyter notebook, it requires four things from the outside world. In a sense that you require a browser connection, you require the physical GPU, you require a place where you need to save the files, and you require enough memory for data loading. Now, none of these, right, actually are directly wired or directly pipelined, right? So, keeping this thing in mind, let us try to work on and see session 2, which basically talks about how can we come up with a deterministic environment using Dockers, and in that, how are we going to use a containerized Jupyter notebook, okay? So after this session, right, we'd be able to understand the three levels of pinning, right? What does pinning mean? And how do you actually generate a log file with pip compile? So we have been using pip, right? Pip install torch, pip install TensorFlow, so on and so forth. But why do we use pip compile? Okay, and how do we use it in a Docker file for hands-on applications? Then how do we pick a compatible CUDA driver framework version using the compatibility chain? And how do we come up with a multi-stage build for production images? And how do we launch a GPU backend Jupyter container with correct volumes and shared memory as a hands-on for this session, right? So this is a major drift problem. So many of my sessions, I will concentrate on very specific things which are needed for us to actually do good production level development using Dockers, Kubernetes, and so on and so forth, right? Uh, I assume that certain initial course on Dockers or certain initial things on Kubernetes, people should know, because we are trying to use those things actually for developing applications which are AI intensive, right? So there is this drift problem which everybody of us know actually, and why when you say pip install torch is not reproducible, right? So this basically means that when you have this pip install torch executed on your system, it will install the latest torch, let us say, okay? So that basically means you are not pinning anything, right? So what effectively means is when you use that type of installation command, it resolves to whatever is the newest today, right? It basically is a transitive dependency that floats to. So two builds a week apart can differ in dozens of packages. So this is where pinning matters, right? And when I say we pin and then we lock it, what does it mean? This means I am installing just not torch, but I am specifically installing, let us say, torch 2.11.2, right? So this basically means that every transitive dependency is also pinned, okay? And we also use, right, hashes, and I will discuss this in some of my next slides, wherein why this is so important. Even after pinning, right, there might be situations wherein, okay, the same environmental files are not there, right? This we'll discuss, but for the time being, let's try to understand that we are going to use pinning. We will pin and then we will lock. So the basic idea here is that we need to solve this drift problem. Diff problem basically says that we need to use reproducible environment so that everybody can use the same type of environment when they use the application, right? So there are these three layers of strictness, right? And that is called as the pinning ladder. So what effectively here it means is we are trying to talk about ranges wherein we tell torch should be greater than or equal to 2.10 and it should be less than 3. Okay, so that basically means that any version or any variant which varies from 2.10 up till 3, okay, can be used. So it is basically flexible. It is a drift obviously, but it is okay for libraries and it's very risky when you are using it for training mechanisms. Okay, so your PyTorch, you have developed some model and you use it for training. So the ranges you need not pin. You have to be very exactly pinning the torch version, right? So exact pins, that basically means I give torch should be installed, which is 2.11.2. It is repeatable install while wheels stay published. So this basically means we are talking of the versions, right? When I say wheels, these are basically the versions, okay, of the same packages, let us say for just CPU, for GPU, and then it will check which driver, okay, you are installed, which version of CUDA you are using. Okay, all of this basically have to be tallied and they have to be universally tuned so that they work hand in hand, right? So that basically means this is a repeatable install. Okay, and once the third one is a very strict thing which talks of hash locked. It basically means it is tamper proof. Anybody tampers with anything, it is tamper evident. It is supply chain safe. Okay, so this is how basically hash lock pinning is required, and we'll see what does it mean when we do some hands-on. Okay, so now the lab basically will talk about lock file workflow with pip compile. So here, this particular thing which we are using, which talks of something called as pip compile, generate hashes requirements in, okay? And this basically means that if you directly use a requirements file, okay, for example, requirements.txt is there, okay, it will try to install basically the things which you want it to be installed. For example, we have requirements.in which talks of torch is equal to 2.11.star, transformers should be greater than or equal to 4.50, and certain data sets need to be, let us say, pulled into my container, right? So now the point here is when I just use requirements as it is, there is a issue of what type of actual torch I am going to install based on the version, and transformer also is a range, right? So now to solve all of this, what we do is instead of directly using pip install torch is equal to 2.11. Whatever, because it will again change from person to person, right? So I do something called as pip compile generate hashes requirements.in. So what is it going to do? It's going to take my requirements.in file, okay, and generate, okay, the requirements.txt, which basically is a very high level of pinning, okay, high level of pinning, and then it also has the hash generated. So now this basically means that whenever anybody uses this type of a mechanism, even though you have the requirements file .n, everybody uses pip compile generate hashes, and once it is generated, you generate a requirements.txt. Anybody who uses this thing, right, will obviously be installing the same package along with the same hash values. So it basically means it is even byte equivalent. Okay, you will not have anything additional. Okay, so that's what it means when you talk about how do you lock using pip compile. Okay, so now let us try to understand the compatibility chain. Okay, so host driver, you have this CUDA toolkit in the image, and then you have CUDA of framework wheel. So that basically means that you have Python version, okay, and that Python will have a wheel which was built for, let us say, 3.12. Okay, so that basically means that you have got 3 or 4 things to be aligned basically, right? You have to have a driver which is installed on your laptop or your own system. That driver should support the CUDA version. That CUDA version should also support the total framework, CUDA toolkit, everything, and then it should link also to the Python as compatibility thing, right? So we need to pin all the 4 when we try to program at the driver level, at the CUDA tag level, at the framework wheel level, and the Python level. Wheels encode their CUDA. That means the plus CU130 suffix / index URL is part of the pin. Document the driver flow in the README file. It is one of the things the images cannot carry. So in the README also, you need to put as to which particular driver people should be using. We'll see that when we do the hands-on. Okay. So now let us try to understand and go to the hands-on. See here, this is the second session, okay, folder of week 2. So week 2 containers, the first one was the last session, this is this session, and in this, if you see, we have got 2 things actually: Docker file, Docker compose, requirements.in, requirements.txt, and this GPU test Python notebook, right? So this is what is visible here. Now, from the README, if you go, I have written the commands which you are going to execute, right? So in this particular folder, okay, you have got Docker file, the Python notebook file, requirements.in, requirement.txt. Now let us try to see requirements.in. Okay, requirements.in basically talks about, okay, what are the dependencies, right, which I need to use, or whatever are the libraries or whatever I am going to install, okay, as a requirement. Now requirements.txt is generated using pip compile command, right? So this is what basically it means. I have just put it. So once you use that, it is generated, and you have to use this requirements.txt to install and create your own container. So my Docker file will have all of this. So it's a Jupyter development container with GPU access and pinned dependency. My Docker file I'm just trying to discuss. Okay. So here it is a multi-stage build, and its layer ordering, okay, is also done. So let us try to understand. We are using NVIDIA CUDA 12.1.0, CUDN 8, and development environment is Ubuntu 22.04. is a builder. From this, I have taken everything. Okay, so CUDA development images has compilers, but it does not have Python. So I will have to install the Python which I want. And then I create an isolated environment. Okay, and then we install the dependencies from the fully pinned requirement, and from the requirements file, okay, we have to install CUDA 121. As I told you in the previous slide, CU130 is a wheel. Okay, I am installing CU121 here. Okay, so there is this runtime, again the same thing. Okay, now this is a port. As I told you, you are trying to run the container, okay, and that container has to have 2 or 3 things from the outside world, right? As I told you. So container in totality is an isolated thing by design. So you need to now have a browser connection to the container so that people can use Jupyter Notebook, right? And you should have a GPU because you're supposed to be running a GPU workload, right? And you need also place to save files also somewhere, because container per se will not have too much of memory. Even if it has, once you come out of the container, that particular thing is lost, those files are lost, right? So what effectively people try to do is, people try to create a volume, okay, on the local system, and that volume has a folder, and that folder actually maps to a folder or gives you a link to a folder which is inside a container. So what effectively happens is, whatever you put into your container, run everything, that particular thing is saved as a container, as a volume on the local disk of yours, right? And you can use it whenever it is used, right? So this is how basically the command line thing, Jupyter Lab. So this is my port ID, there's no browser, IP address, so on and so forth. And then this is the Python program, right? So what we will do here is, I have written as in the README file, for the first time when you're running, you should use docker compose up -- build. Then every time you start, you will use docker compose up. And when you want to stop, you will have to use docker compose down. Okay. So now once this is the case, I have actually done, okay, docker compose up, because the first time I ran, I used docker compose up build, so it has built everything, the container is ready. And now every time I use, right, I use docker compose up. So here you see the container has executed. You have this thing generated wherein, as a result, so CUDA version 12.10, you have a container image copyright, this, that, everything. Okay, so this is how it's going to happen. Everything is done. Server app, Jupyter Lab extension was successfully loaded, serving notebooks from the local directory. Okay, Jupyter server 2.20.0 is running. And if you see here, if you link, this is where it basically is running. Okay, so if you run this now program, okay, I'll run it again. I had run it, so it's showing me the result. Now if I run it again, see here what I have tried to do. I have tried to import torch. I have tried to see whether this is a CUDA wheel which is installed or a CPU wheel which is installed. So my CUDA wheel is installed. So I am also trying to check whether GPU is present or not, and what type of version of torch is installed, with lot of other things. And let us print Jupyter is alive inside the container, because inside the container now I'm able to run the Jupyter notebook, right? So this is how it's going to execute the program. This is the program. It simply tells that I have now configured a container which can run a Jupyter notebook, okay, and which is deterministic in nature, because the environment wise I have used pip compile option, and everybody who uses this type of a command along with this particular demo folder will get the same packages, same things as in the requirements.txt file without any variation. Even there would be not be a variation in byte size, so byte strictness is maintained. Okay, so this is what is the session hands-on for today, and let us continue with the slides now. So okay, so now here basically we are talking of multi-stage builds. As I have told you that you run the pick wheel and requirements.txt, and the second thing is you basically can generate your own requirements. Okay, in case you don't want to make your container very heavy or bulky, right? So the basic idea is runtime images can be actually shrinked. So, smaller image you generate, you have a faster node pull and faster auto scaling and faster job starts. So that basically means that from the image size aspect, you can have two types of multi-stage builds. So one is this, when you're trying to compile it, you do a compilation wherein which is a bigger compile, and then you can actually split it up into two stages. Okay, and that is what it means. Okay, so now I told you about the containerization of Jupyter Notebook. And when I told you we require four things, right, inside the container, since it's isolated, and we require some things from the outside world. So I told you about three things. We require a browser connection, we require the actual GPU, and we require the memory for storing the information as well as storing the files, right? So when I say we have to connect, right, our container to a browser, so I need certain binding to be done. Okay, and I need to publish the port, right? And I use the token URL to actually access that. Okay, for the browser. So this is what we have done. And the data thing, we actually do the mounting actually. So workspace notebook survives the container, images stay stateless. So that basically means you are going to link the folder of yours which you are using in your container and map it to a local folder on your system. Correct? So it is something like a virtual folder which you are using from your local hard disk, right? And when I say the memory size, so that basically means in parallel the data should be loaded to our container. So that's what it means. It is shared memory. Okay, size is 8 gig. So that basically means I am trying to parallelly load my data onto the container. Okay, and when I actually execute it on a GPU, right, I need to again parallelly send my data to the GPU, right? So the basic essence here is that the container is disposable, whereas the volume is not. So that basically means once I shut down my container, okay, whatever is the data, it will be lost. Okay, otherwise I will have to again recompile my container using all of that. It becomes a very heavy container. So what I do is I have a local storage. I do everything on the local store or a local data thing, and I can dispose the container. So the basic idea here is treat every notebook server as a cattle, not as a pet. Okay, so that basically means the cattle can come and go. Okay, but you need not keep everything as a pet with you. So that is what effectively it means. So as I told you again, we can run the Dockers and then we can do whatever GPU we are using. Okay, SHM size, all of this. and then we can verify the GPU name prints, and we are trying to use the local host, okay, the token number, so on and so forth, okay. So the basic idea here is we are able to run the program. So I showed you the program already, and when I say bind mounted and baked in, so the basic idea is where will the code live, in the sense the GPU notebook code which I now generated, this is just a 4-sentence code which talks about trying to import PyTorch and trying to see the version number and then trying to print something. Okay, so the basic idea here is there are two things. Copy the code at build time. The image alone is deployable. We can basically use the artifacts, right? And basically that is where the DevOps thing come into picture. We will see all of that. And when I say bind mounted or developmental this thing, it means it edits on the host, runs in the container, it gives us instant feedback. We pair with an editor that attaches to containers. So we're talking of dev containers. We'll see what does this mean. So we have got, let us say, the same image. It works in two modes. Mount over the workspace during the day and rebuild to freeze a version. So this basically means that you basically work at your own workspace during the full day before you basically freeze a final version, which basically can be used by others. Okay, so you need not go on working on at the inside container level memory, but you work at the workspace of your host full day, and then before final freezing, okay, you freeze that version along with the container if you need for shipping it. Okay, so that's what it basically means. Okay, and this is the basic idea of Docker ignore and certain things. I am talking about certain data sets which do not belong in the images, okay, and there are certain build context which actually is the .env thing, okay. So the environment thing or the copy persistence in the layer basically is always secure or always known to people, okay, even if it is deleted. So this is what basically the idea of trying to use certain commands which are more secure in nature for trying to do a more secure thing, but we'll not go into those detailed things now. But for the time being, we should know that Docker ignore and secrets are certain things which we might use. Okay. So one of the things which I want you people to concentrate on, and maybe send us some comments if certain queries of yours still exist related to this particular session. So I want you to convert session 1's image to a locked build. Session 1's image is that particular smoke test image, okay, to a locked build requirements.in. Then you use pip compile, generate hashes, and then you install that, then launch the Jupyter from it with the GPU volume and 8 GB SHM. Okay, so this is one exercise which I feel you should do before we start the next session. And if any doubts are there, you can message me and we will try to answer, right? So from the understanding point of view, let us try to understand if two unpinned builds, okay, run with a gap of about a month, okay, what can change or what has changed, okay. And this is a very, very important question as to why must the wheels CUDA suffix match the images toolkit. This I told you, this is a very, very important thing for trying to develop your whole framework, because everything needs to be synced. This is a hint. So we need to understand that, okay. And why does the data loader care about SHM size? So this basically means these are certain things which you should be able to answer. And so before we start the next session, I expect you to be answering all that and try to do that exercise. Okay, if needed, I'll show you the solutions. Okay, yeah, thank you.